Okay, everyone, we're going to get started. So thank everyone. Thank you all for coming to workshop number 2. I'd just like to note at this time that we are recording this call for the purposes of replaying it for others who weren't able to make it at this particular time. So I'm going to start sharing my screen now, and we can get started. So in terms of the agenda for today, I'd like to give you all some updates on the development of the heRo3 platform. Then we can spend a little bit of time talking about a few important tips and tricks for how best to use heRo3 and how to build certain types of functionality into your models. Then we will move into an open Q&A session where you can ask any questions that you might have about how to do things in heRo3. And then we will close with just a short message about the best way to get support if you have a problem with the platform that you'd like to get resolved, or if you have any feedback that you'd like to provide. So, updates. As you may know, pilot testing began in late November with our initial release. And that provided support for developing Markov cohort models only. We then had a major update in late December, which allowed users to build partition survival models. And then more recently, in January, we added functionality for running value-based pricing analyses. And so that was the most recent update. In addition to that more recent update included the ability to export tabular data to CSV or XLS files, as well as the ability to export your model as an RStudio project so that you can run it on your own machine in R. And so that's sort of what we've been doing recently. The next update that we are working on should include functionality to do deterministic sensitivity analyses. And of course, this is a living platform that gets updated as we go, so expect more features and fixes to roll in as the pilot testing continues. Jumping into the tips and tricks. One thing that is very useful to be able to do is to have a
Something live. It's not updating to everyone else.
It's not updating?
There we go.
Oh, sorry. There's a bit of a lag in the slides, so just bear with me on that. So one of the things that can be very useful to do is to create a parameter or variable whose value depends on the strategy that it's being evaluated for. And the way this can be done is using a function called dispatch strategy. And so I want to just give you a quick example of how that can be used and how it can be helpful in building your model. So I'm going to switch over to the heRo application right now, as you can see. And so I've opened a model that takes advantage of this functionality, and right now I am in the variables page. And so I want to just sort of look at what's going on with this model. So first off, we are defining a probability of death here based on a survival distribution. So you can see here we're using the function define survival here to create a survival distribution, a Weibull distribution, using specific shape and scale parameters. Apologies, this is the wrong example. Down here that I meant. Great. So this formula, this variable, P underscore FABN, this is the probability of febrile neutropenia. And this is something that's going to differ by strategy. And the way this is set up is there's this baseline probability of getting febrile neutropenia for chemotherapy, and then that is multiplied by a relative risk here, which depends on strategy. And so for chemotherapy, since this is a probability for chemotherapy, we're setting the value here to 1. For targets, we're setting it to the value of this parameter, RR underscore FEBN underscore target. So this is just a relative risk for targeted therapy. And for immune, we're setting it to another parameter value. And so this function call is a dispatch strategy. The way it works is each one of these arguments, each one of these named arguments, is a value for a particular, that it will take on for a particular strategy, where the name of the argument corresponds to the strategy that it's being set for. So you can see chemo equals 1, so the relative risk here, this part of it, will evaluate to 1 for chemotherapy, it will evaluate to this value for targeted therapy, and it will evaluate to that value for immunotherapy. And these names here, they simply come from the names of the strategies. So if I go over back to the strategies page, you can see those are the names I assigned to the strategies. So those would be the argument names that are used in the call to dispatch strategy. And so what this allows for is here we have, down here in this call to dispatch strategy, we've defined a single variable that will take on a different value, an appropriate value for each strategy. And so no matter where we reference this, it will reflect the appropriate sort of probability of getting this adverse event for any strategy. And so that's a very useful thing that you can use, and you can use this anywhere. You can use this in the variables page. You can use it in sort of the transitions page and the formulas there, over in the transitions page. You can also use it in the values page. So anywhere where there's one of these formula inputs where you want to make something depend explicitly on strategy, you can use that, and that particular formula will evaluate differently by strategy. So another important tip is multi-column lookups. In workshop number 1, we described using the lookup function in heRo3. And the way we describe it is by comparing it to the VLOOKUP function in Excel. However, one key advantage that lookup has in heRo over VLOOKUP in Excel is that you can look up on multiple key columns simultaneously. So if you've got a long-form data table with multiple sort of key columns, you can do a lookup and say, I want this value from that column, this value from that column, and then it will pull the appropriate row, the value from the appropriate row. And you know, that can allow for much more complicated lookups than Excel can do. And so let me just give an example of that and a case where it can be useful. So I'm just going to go back to heRo and load up an example. So here we have a data table of different doses for different strategies. And you can see that both of these strategies have doses that differ over time. So we've got a column for strategy. So these are the doses for targeted therapy. These are the doses for chemotherapy. There's a column for month because, of course, the dose is changing over time. So, you know, for the first month for targeted therapy, the dose is 800 milligrams. For the second month, it's 700, and so on. And then finally, we have our value column for dose. And so what we're going to do is we're going to set up a lookup which tells it, you know, I want to pull the dose for a given strategy and for a given month. And we can look up on both of those columns simultaneously. So going to the variables page, I can show you how that's being done. So in the variables page, we have a variable here called dose underscore chemo. And we'll take that one as an example. So I'm going to open that up in the formula editor. And you can see we're calling lookup here. And so the first argument that we pass in is, of course, the table that we're looking up on. And that table was named dose underscore table. And then we pass in the column names that we want to look up on. So, for example, we want the strategy column to look up a value of chemo, since we're looking this up for chemotherapy. And then we want it to look up the month that matches the current model month. And then our value column is dose, because that's the column that we're going to pull the dose from. And then finally, we pass in the argument bin equals true, because when we look up the month, we want to make sure that it looks up sort of the most recent month, and so if we're doing a weekly model, for example, and we're on week 2, then we wanted to pull up the appropriate dose from month 1. And so this will ensure that that happens. And so here we have just an example of a lookup where we can take a long-form data table with multiple key columns and look up on those multiple key columns simultaneously. And so this is also useful if you have a life table that's done long form where you have sort of a column for age and then a column for gender and then a column for the probability of death. You can also use lookup there to sort of pull the appropriate mortality rate for a given age and gender. So the next tip and trick I want to talk about is time to discontinuation. And this has come up a bit in feedback that it's not clear how, if you're doing a partition survival model, how to handle time to discontinuation. And so often in a partition survival model, it's not sufficiently accurate to model discontinuation based on progression-free survival. So in other words, it may be the case that some patients stay on treatment after progression, or they may discontinue before progression, and so that needs to be modeled separately from PFS. And so I want to go through a quick example of how that can be modeled in heRo3. So I'm going to go back to heRo, and I'm going to load an example model and walk you through it. So first, I'm going to go to the variables page and look at our survival distribution. And here we have a series of survival distributions defined. Of course, we have our PFS distributions and our OS distributions. But additionally here, I've defined a distribution for time to discontinuation. And I'm, in this case, simply defined it as a Weibull distribution with certain shape and scale parameters. But in principle, we could put in anything here. We can use all the tools that we have for modeling survival, and we can apply those to time to discontinuation. But we'll just take this as our time to discontinuation distribution. And then, going to the values page, I want to show you how we calculate the medication costs using that distribution. So here we have a couple cases. So for this model, what I've done is I've assumed that for chemotherapy, we need to model time to discontinuation separately from PFS. But for targeted therapy, we're just modeling it based on PFS. And so those look a little bit different, so let's do a quick comparison and contrast. So I'm opening here the entry in under med costs, which is tracking our medication costs, for chemotherapy. So let's take a look at the formula first. This part right here, this function survprob, is calculating the probability of survival for a survival distribution. So it takes, first argument is the survival distribution that we're using to calculate the probability. And then the second argument is the time for which we are calculating the probability. And so this call right here will generate for each model cycle the probability of survival, or in this case more specifically, the probability of still being on therapy, since we're passing in the time to discontinuation distribution. And so obviously this is important for calculating our medication costs because among all patients in the model, this probability is the proportion who are on therapy. However, there is one slight sort of caveat there, which is that because we're modeling time to discontinuation and overall survival separately, we need to make sure that no matter what we put in for TTD, that the probability of being on therapy is no greater than the probability of being alive. One certainly wouldn't want to create a model where patients who are dead are still being sort of treated as being on therapy. And so what I'm doing here is I'm using the pmin function to take the minimum of the probability of being on therapy and then the probability of being alive, which I'm just generating from our OS distribution. And so this part of the function call here will take the minimum of the probability of being on therapy and the probability of being alive. And then so we take this component and then we multiply it by the cycle length in months, and then this variable, which is the cost per month of the medication. And so this formula will calculate our medication costs for chemotherapy based on this time to discontinuation distribution. And it's important to note when we set it up this way, under state here, we need to put it as all because we're not modeling medication costs as a function of what state patients are in, at least in terms of pre-progression, post-progression, we want to make sure that this cost is applied irrespective of state. And so when we're using this sort of approach of using time to discontinuation, the state needs to be set to all. By contrast, here for targeted therapy, we're just taking the typical approach of modeling medication costs, assuming that they only occur in the progression-free state. So the state is set to progression-free, and we don't need to worry about sort of calculating the proportion of patients on therapy because we're assuming that if they're in progression-free, they are on therapy. And so here we're just multiplying the cycle length a month times the cost per month of targeted therapy. So I'm going to stop here for questions since this was a bit of a complicated one. So if you have any questions about how this was set up or other ways to, other sort of cases that you might want to consider for time to discontinuation, please chime in with your questions. Okay, moving on. Next thing I want to talk about is indicator variables. And so often in a model, it's important to be able to switch between two different data sources that you're going to use. For example, if you're doing a partition survival model, you may want to switch between, be able to easily switch between different parametric forms. You know, maybe you've got a model where you've estimated an exponential distribution as well as a Weibull distribution, and you want to be able to, you know, sort of change one variable and then make it toggle between the exponential and the Weibull distribution you've estimated. Or maybe you have two different tables of utility values. You know, one comes from a regression that you've run and another comes from some published source that you have, and you want to be able to switch between those two pretty easily. And so the way this can be accomplished right now is through the use of indicator variables and combining them with some conditional functions. And so let me give you an example of what I mean by that. So I'm going to open up my example here. And so I've opened up a partition survival model which demonstrates switching between a different pair of different survival distributions. Okay, yes. Okay, so over here I've created a parameter called PFS_dist. And this variable is just simply a text string that I put in which determines which distribution I want to use. And so this can either be set to Weibull or it can be set to exponential. And so this is going to be the control that I use to switch between those two distributions. And then let me show you how I implement this elsewhere in the model. So I'm going to the survival distribution page. And here you can see I've defined my Weibull distribution. So this is called PFS_chemo_Weibull. And here I'm just defining it as a simple Weibull model with a given shape and scale parameters. And then I also have another model here for PFS, which is an exponential model. And these are the two models we want to be able to toggle between. And so the way that works is I set up a third distribution, which I just call PFS_chemo. And then in the formula, I use a conditional statement, which will check the value of PFS dist. And if it's Weibull, it will use the Weibull distribution. And otherwise, it will use the exponential distribution. And so it's really as simple as that. So when we go to the model results, you can see here that I've currently set it to exponential. If I change this to Weibull and make the model recalculate, you'll see the PFS distribution will change to the Weibull that I've entered. And so just using this override value here, I can just toggle back and forth between the two. And so that way you can have both of those models, both of those survival distributions coexisting with the model and easily toggle between them. Now, there's one caveat that I want to add to how to set up the conditional part of this. So there are two different ways to set up conditional statements in heRo, and it's important to use the right type of conditional statement in the right circumstance. So right now, where I've set this conditional up, it's in the survival distribution stage. And if you do this in the survival distribution stage, what you want to use are the if and else statements. And the way that works is you have an if statement, which is in parentheses, and then within those parentheses, you put in the condition that's being tested. And then the first value here is whatever is used if it's true. There's an else statement, and then followed by the value if it's false. And so if you're doing a conditional statement on the survival distribution stage like this, you should use an if-else statement. If, however, you're doing it on the parameters page, you should use the if-else function. And the way that one works is you type in if-else, call that function, and then that if-else function has three arguments. It has a condition, the value if true, and then the value if false. So if we were, for example, having a utility value, which varied based on some indicator variable, and we were doing that on the parameters page, then we would use the if-else function. If we're doing it on the survival distributions page, then we use the if and else statements. So, moving on to the next item, creating survival distributions. And this is something that was talked about a bit in Workshop 1, but now in Workshop 2, we want to give a little bit more of a comprehensive overview of all the different functions that are out there for defining survival distributions as well as modifying them. So we're going to quickly overview those. And then we're going to look at a model which uses some of those functions to sort of show some complex behavior. So, getting into the functions for creating survival distributions, there are a few different cases. So if you're starting with time to event data, in other words, event and sensor times, you can do a couple different things. First, if you want to generate a Kaplan-Meier, you can use the servFit function, and that's a function that comes from the survival package, which you can look up. It's not part of sort of heRo per se, it's just sort of a general R function for generating Kaplan-Meiers, but you can use that function to create a Kaplan-Meier distribution, and then that Kaplan-Meier can be used in your partition survival model or Markov model. Similarly, if you want to generate parametric survival distributions, there are a few different functions available. So first there's the flexServReg function, which is for simple parametric models. So that's for doing things like exponential, Weibull, log logistic, log normal models. There's also the flexServ spline function, which is for fitting restricted cubic spline models. And both of those functions come from the flexServ package, FLEX-SURV. And so we can provide documentation to that package offline. But both of those functions are supported for generating survival distributions in heRo. And then additionally, there's flexServCure, which comes from the flexServCure package. And that is for fitting mixture and non-mixture cure models. And so all of those options are available for parametric survival models in heRo. Now, if instead of starting with time to event data, you're starting with a table of survival probabilities, something like, for example, output from Kaplan-Meier that's previously been run, you can enter this as a table and then use the function defineServTable to turn that into a valid survival distribution. And essentially what that will do is it will do a lookup on that table, and it will look for the column called time and the column called survival, and it will look up the appropriate survival at the appropriate times. Now finally, if you have already estimated parameters for a given parametric survival distribution, you can use the function functions define survival for simple parametric models, define spline survival for restricted cubic splines, and then define survival cure for mixture and non-mixture cure models. And so those three directly correspond to flexor of reg, flexor of spline, and flexor of cure that we described in how you estimate parametric models from time to event data. And so those are the equivalent functions, except instead of estimating the parameters, you just directly plug in parameter values that you already have. And so all of these functions that are on this page are used for creating survival distributions. Now, we also have a series of functions for modifying survival distributions. In other words, for taking one or more survival distributions and using them to create other survival distributions which behave differently. And so let's cover a few of the cases for modifying survival distributions. So one case is for setting the covariates for a model. And what I mean by that is, say that you've estimated either a Kaplan-Meier or one of those parametric models, and it has a covariate for treatment. And so once you've estimated that model, you get a single model which actually reflects survival for multiple separate groups of patients. And so in order to use that model, you need to sort of specify which groups of patients you want to generate the predictions for. And so that's what this covariates does. You use it to take a model that has multiple sort of covariates defined, and you set exactly what the values are for each one of those covariates that you're going to generate predictions for. And so, for example, we've got a model that predicts survival based on treatment group. Then we need to use set covariates on it to specify which treatment group we want to generate the predictions for. The next case is applying a treatment effect, and we have a number of functions for that. So we have apply HR if you want to take a survival distribution and apply a hazard ratio to it. We have apply AF for applying acceleration factors, apply OR for applying odds ratios, and then apply shift for shifting a distribution forward or backward by a fixed amount of time. And then finally, we have a set of functions for combining two or more distributions into a single distribution. For example, the join function allows you to take two or more survival distributions, and sort of knot them together at specific points in time. And so, for example, if you've got a Kaplan-Meier distribution that goes out to 20 months, and you want to combine that with a parametric model to project beyond that time, you can join those two distributions together at 20 months. We also have the mix function, which allows you to mix two or more survival distributions together using the specified probabilities. For example, if you wanted a survival distribution that reflected, 20% of patients using one Weibull distribution and 80% using a different Weibull distribution, you can use the mix function to do that. And then finally, we have the add hazards function, which combines two or more survival distributions together as if they represent independent risks. For example, if you have a survival distribution which represents disease-specific mortality and another one which represents sort of general population mortality, you can combine those using add hazards to reflect all-cause mortality. And so that's a lot to digest, but let's do a simple example which sort of provides examples of how to use some of these functions. And so I'm going to go back to heRo, and I am going to open up an example model. And so I'm going to go to the survival distributions page and walk you through how overall survival is modeled in this model. So first we have a distribution here called gen-pop mortality. And I don't want to get into the formula behind this one because it's a little bit complicated. But what this is going to do is it's going to generate a survival distribution that reflects general population mortality for our patients based off of their current starting age and probability of being male. And we can actually cover exactly what's going on behind the scenes here. But what's happening there is going on in the code editor, so it's a little bit more of an advanced example. But in short, this survival distribution reflects general population mortality. Next here we have our overall survival that reflects sort of mortality from the disease in question. And so looking at the formula here, you can see that I'm using the flex cure function to fit a parametric cure model, a Weibull mixture cure model, to some time to event data that has been entered into this model. And so TTE data is just a table of event and sensor times for the two treatment groups. And you can also see here that the way I've set up the sort of survival model here, that treatment has been specified as a predictor. And so this is a model that models survival as a function of treatment. And so this is a case where we need to use set covariates, because this model, as currently specified, will generate predictions for both chemotherapy and for targeted therapy. And when we use it, we need to specify which one of those treatment groups we want to use it for. And so under here, you can see there's a survival distribution, OS chemo, and here I'm using set covariates. So I'm using set covariates on our survival model, our cure model, and so that's being passed in. And then next I'm passing in that the treatment group I want to generate this for is chemotherapy. And so this is just the name of the treatment covariate, and then this is the value I want it to take on. And then I'm also passing that in using the pipe operator into the add hazards function, which is taking this survival distribution, which represents the disease-specific survival for chemotherapy, and it adds on top that general population mortality that we defined previously. And so OS chemo represents disease-specific survival for chemotherapy with general population mortality added on top. And similarly for targeted therapy, we do the same thing, except we set the treatment group to target. And so this represents disease-specific survival for targeted therapy with general population mortality added on top. And so using these survival functions, you can do some very sort of complex stuff, and just providing an example of what that looks like here. So you can see here survival is sort of initially there's a very high rate of hazard, but over time patients get start to be cured, or rather the patients who are cured tend to be the ones who are left remaining, and the patients who are not cured are dying out fairly fast. And then we reach a plateau here as practically everyone who's remaining is cured. Except over time the patient population ages and the general population mortality increases, and so the hazard rate starts to go up again. And so this is the kind of very complicated sort of behavior of a survival function that can relatively easily be put together using heRo. And of course there are a lot more examples in this that are possible. It's not really practical to cover every combination of these functions that could possibly be put together, but really the key here is to understand what each of these individual functions can do, and then string them together to get the type of behavior that you're looking for. So with that, I'd like to stop for any questions that you may have, either about any of these examples or other questions that you may have. So please feel free to just speak up if you have a question.
Hi Jordan, it's Dom here. It's not a very important question, I suppose, but you mentioned earlier that you have two different types of syntax for if and else, depending on which screen you're working on. Why is that?
Okay, yeah, so let me clarify that. So to explain that, we have to understand sort of what these R expressions are that we're writing and in what context they get evaluated. And so let me sort of just go back to that example. So you'll note that on this variables page that we have two separate sections. We've got the parameters section and the survival distribution section. And to explain why we need that, let me first explain the way that parameters get evaluated. So parameters get evaluated in the context of a data table. And that data table has columns for what the strategy is, what the current state time is and what the current model time is. And so when that function, when your expression is being evaluated in the context of that table, it's actually a vectorized expression. So let me break that down a bit. Let's say that we have a function of state time. So I'm just going to write in here. Let's say we have a formula which is sort of if else state time is greater than 5, and then the value is 3, and if not, the value is 1. So when we reference state time here, that value, that expression, state time, is not a single number. It is actually a vector of numbers. It is a vector of every possible state time that we need to evaluate it for. And not only that, it's actually a vector that represents the state time for every possible combination of state time and model time. So if you think about, for example, a model where you've got tunnel states, and let's say our model has 3 cycles. And so there are 3 different values for model time, because we can be in cycle 1, cycle 2, and cycle 3. But there are also 3 different possible values for state time, because we can be in a given state, we can have been in the state for 1 cycle, 2 cycles, or 3 cycles. And so potentially we need to calculate this formula for any combination of those 2 values. And so what we get is this big table with columns for state time and model time, and there's sort of a vectorized process, a vectorized calculation where the entire sort of column of values for state time is inserted into this calculation. Now, sometimes that doesn't matter. If we're just doing, for example, a fixed value here, that fixed value will take on the same value in every one of those rows in that big table. But if we're using a function like if-else, it's important that that function actually works with vectorization. So this function if-else is meant to be to still work if this input here is a vector. And what I mean by work there is that in some cases state time is going to be less than 5, in other cases it's going to be greater than 5, and it has to pull the appropriate sort of value of true or value of false in each one of those cases. And if-else is set up to do that. However, the if statements in R are not vectorized. They expect the condition to be a single value. And what will happen if you put a vector, a vectorized expression into the if statement, so if we were to do, for example, if, and then instead of this we do, and then we do else there. So the way that what would happen here if you did this is that this condition would evaluate once for whatever the first state time is in that table. And then for every row, it would either return 3 or 1, regardless of the actual value of state time in that in that row in the table. And so really it's a question about vectorization and whether if or if else is appropriate in that case. And apologies, that's a difficult concept to explain speaking over the phone rather than visually. It would be a little bit easier if I could send you a diagram that would explain that in better detail. But hopefully that gives you a sense of it. Really the key thing is that is this condition single-valued or multi-valued, and the if-else function is okay for handling multi-value things, whereas the if statement is not. And because the parameters are evaluated in the context of a table with many different rows and it's done using a vectorized process, it needs to be able to accept multiple values in that condition. So again, apologies if the explanation is a little bit difficult.
That's great, thank you.
So actually just one thing that I want to bring up. Half cycle corrections are also an issue that has come up as a question here. And so the way that heRo handles half cycle corrections is to average the trace between adjacent cycles. So for example, in the first cycle, it's the average of the trace at time 0 and time 1. And for the second one, it's the average between time 1 and time 2, and so on. Now, we plan on adding the option to be able to select how you want your half-cycle corrections to be done or whether you want them to be done. And so that functionality will be added shortly. But for now, the way it works is that half-cycle correction is applied automatically, and it simply sort of averages adjacent cycles. But any other questions that you would like to add in or comments?
Jordan, you mentioned being able to extract the model in like a tabular view, like you can do in the regular HEMOD, but I'm not seeing, I don't see where to do that.
Right, so let me clarify a bit. So it doesn't exactly let you extract it into a tabular view. Rather, it exports it as an RStudio project with the sort of the code and the data necessary to run it. And so that's slightly different, but let me walk you through that. So let's just take this model that we're working on now as an example. So we can click on this button here, which takes us to our screen where we can export the model to R. And when we click this button, what's going to happen is it's going to download a zip file, which includes the RStudio project. So I'm just going to open that up. And so you can see, let me zoom this in a little bit. So there are 3 files. There's an R project file, which is just the RStudio project file. So if you click on this, it will open up the project. And then within that project file, there's an RDS file, which stores the data for the model. And then there's an R file, which stores the code necessary to run the model. And that R file will also, it has some code here which can install the necessary packages if you don't have them already. And so we can just sort of run this code here, and then what it's going to do is it's going to load the data from that RDS file, and then it's going to call a function run HERO model, which will run it. And if we do that, then it's going to run the model. You can see it's running here. And because I made a change here that sort of results in the model no longer working, it doesn't work. So this tells you what's going on. But because we've exported it to R, that means we can sort of run this model with line-by-line debugging and see exactly where the problem occurred and see what's going on in the sort of evaluation of the model at that time. So this is what we mean by exporting it to R. Now, we're still refining this functionality to make it a little bit more seamless. And one thing that we may add is exporting it in the format so that you can make changes within R and then take it back to HERO. But for now, the purpose of this is just so that you can run it in R, see what the results are within R, do what you want with them within R, as well as use line-by-line debugging to see, if you've got a problem, get a more detailed picture of where things are going wrong. Does that answer your question?
Yeah, absolutely. That was very helpful.
Great. Any other questions?
Yeah, this is Jinshu from Merck, and I have a more kind of a overview question about heRo3. Now, I'm looking at this is quite different from the previous HERO, built mainly for oncology models. So I'm just wondering, moving forward, are you planning to kind of everything going into heRo3 direction, or you still keep the HERO, I guess it's heRo2, kind of as two separate kind of platforms?
Right. So let me tell you about that. So first, philosophically, there's a difference between HERO2 and HERO3. HERO2 was really about taking a sort of a relatively generic model structure and letting you change the inputs to it. And so we had I guess you call it a moderately flexible partition survival model, and you could do a few things with that. Mm-hmm. But it was really a single model that you were playing with. Whereas with HERO3, the vision is that this is a platform for building models de novo and customizing them the way you want them. And so HERO2 lets you use a model, HERO3 lets you build a model. Now, there's another part of HERO3, though, that we haven't yet developed, but which is part of the roadmap, which is how you will sort of make that model available to others once you've built it. And so one of the nice things about HERO2 was that you had this great user interface where you had the inputs that were on the left, and the outputs that were on the right, and you could just sort of play with sliders and see how that would affect the results. There were some drop-downs that you could change, for example, from a Weibull distribution to a log normal distribution. And I think some users have noted that that functionality, that kind of sort of more elegant user interface is absent in heRo3. And that's because that's part of a different part of the platform that we haven't yet developed, which we call the model publisher and the model viewer. And so what the model publisher is going to let you do is once you've built a model, you'll be able to build a user interface to it using sort of a drag and drop approach, where you can say if you've got a given input parameter. Let's say, for example, we go to the parameters page. Let's say we want to let the user change the shape parameter on this Weibull distribution. Well, once we have the model publisher, you'll be able to create a control that represents that shape parameter. And then you can make it a slider, you can make it a numeric input box, and that control will control the shape parameter. And that will be on the left-hand side, and you'll be able to organize all these different sort of input controls on the left-hand side how you want into different tabs just by dragging them. And then on the right-hand side, you'll have your results. And so that once you've published a model in that way, you'll be able to use the model viewer to view it, and that will be your nice sort of user interface. And so essentially, once that functionality is complete, you'll be able to turn your model into what heRo2 was, right? It's sort of a nice, sort of user-friendly published model where you get to decide which inputs the user has access to and which outputs the user has access to, and sort of control the experience and create a nice package experience, as opposed to this sort of more wonky interface that we have here, which is really built around the process of modelers building models.
Yeah, so the models that that are pushed out, the user interfaces will basically be web apps.
Yeah, okay, all right. Thank you for the detailed explanation. So with that, it sounds like the future for Vision 3 will have that interface feature that's similar to heRo2. So then are you envisioning you're going to decommission heRo2, just keep it the way it is? But
we have already taken heRo2 offline.
Yeah, if you're in heRo2, you must be sneaking in through the back door. Yeah, and part of the reason, Jordan has explained some of it, but it's also that all of the analytics in heRo1 and heRo2 were hidden from users, and it's why we felt we hit the wall with it, that people liked the interface, but it did not have transparency. So a precondition for heRo3 was that people need to believe and trust what's running under the interface. And that's why the first step is the model builder, and the model builder is basically pointing to an open source validated R modeling package, because that's really, you know, it's the web interface, but the fact that all the analytics are being done with validated code. And it's that combination, if we can gain acceptance in the modeling community, HEOR community, of the validity of that value proposition, then we think we can move to the user interface and the publication of those or the dissemination of those as web apps, as opposed to an Excel file attached to an email or however, you know, on a SharePoint server or whatever. So it's a radical break from how models have been disseminated in HEOR, and we don't want to get too far out ahead of the parade. So the first step is gaining acceptance for heRo3 as a model builder and a platform for doing very highly sophisticated analytics. And if we can gain acceptance for that, then going to the user interface as a web app is I don't want to call it trivial, but we've already done a lot of the design work on that.
Yes, absolutely. Thank you for that. So do we have a rough idea when the what you call model publisher will be available, that feature?
Well, that gets the whole issue of the sustainability of, you know, this whole platform. In discussions with academics and HTA bodies, it's been very clear that if this is going to gain acceptance, we need to make this available without charge to nonprofit agencies and academic institutions and students. So that means that it's basically the for-profit sector that will need to support this, and if there is not an adequate number of companies and persons who feel that this brings value to their work and to their enterprises, then it ceases to be sustainable. So it's a very difficult question to answer. We would love nothing more than to double the size of the development team and get the model publisher going on a parallel track such that we could provision it pretty quickly. But it's going to come down to the economics of it.
I see. Thank you so much.
And I would note that, if I may just for another moment, that there's also some discussion or extensive discussions that we're having in-house as to where the value of this platform lies, and you know, some have taken the position that it's all about early modeling and the ability to develop a model in 15 minutes, a half hour that otherwise would have taken days in Excel. That's where its greatest utility is, and there are others who sort of have also argued that it's about moving to a new paradigm for the use of models and how we disseminate models, namely as web apps. So, to the extent that we remain, I think, completely up in the air about what the right answer is, we certainly would appreciate your feedback and your input, how you envision this, let me dare I say, a disruptive technology, how you think it would bring greatest value to your own practices and professional lives.
Yeah, I would just add to that really the vision for this platform is that once you've built a model, there's no limit to how that model can be used afterwards. And so, once you've built a model, the plan is ultimately to make these models, so their results, available as a service to anything that wants to use them. You deployed it within your firewall, your corporate firewall, for example. Other applications behind the firewall would be able to sort of get the results from a model and use them to display them in some other application, or collect the results from models in some other database. And so really the goal here is to create a totally open platform where once a model is created, it can be sort of used in any number of ways. That's a vision that I think we can absolutely execute on if only we can get enough support behind us. And so right now we want to convince everyone that this platform has the analytical firepower to do everything it needs to do. And if we can generate that support, then there's really no limit to what these models are going to be able to do. We just need to build up that support.
Jordan likes to eat.
Yeah, I wouldn't use the word disruptive, but this is certainly revolutionary. And anything we have this kind of breakthrough or paradigm change, it takes time, and it takes practice, it takes people, and it takes the whole village to move the mountain. So I actually feel that heRo3 has a great appeal just by the ease of use in oncology and the friendliness of the interface. So I wonder what kind of feedback you get from heRo3. Definitely the not being transparent is something you just mentioned, but I think that actually comes with kind of a trade-off that anytime there's something easy to use, then the downside is it could be that it's not easy to see what's under the hood and all that. So you do have that trade-off. But I wonder, how acceptable users are for heRo3. I think that certainly still has its appeal.
Oh, people, I mean, I think in general I can say people loved the interface of heRo3 because the ability to look at inputs and outputs at the same time, any possible pair, it gave you an understanding of models that simply was not possible with the backward and forward, linear navigation in models in Excel. So there's no question that cognitively it's a game changer, and as Jordan has indicated, this is within reach for heRo3. We've already, in fact, developed the drag-and-drop technology to build UIs, on top of heRo3. But if people don't accept the basic engine, the analytic framework that you're looking at, a model builder in heRo3, then it just becomes a black box, and again, of limited utility, I think, other than, it's a pretty interface.
Yeah, but I'd note that ultimately, if we're successful and we get to the support we need, you're going to be able to essentially build Hero Oncology 2 within heRo3. I mean, that's going to be sort of the power and flexibility of it. And so, Hero2, I think, was an important milestone. But heRo3, I think, is going to totally replace it and not only do what heRo2 did, but do all kinds of things that heRo2 couldn't.
Yeah, so I know our team has been asking for examples that is a little bit more complicated than the ones on the template. So if you can have more examples for example, in oncology, that would be really helpful.
Can you it would be very helpful. As a matter of fact, we were talking about it earlier today at a team meeting. We'd like to put up templates that would address use cases that people confront. So if you have any suggestions right now, that would be great. If you want to do it after the workshop, that's fine. But, we would love to get suggestions from all of you of use cases, because we figure if we put up the first one, then the second, third, and fourth ones you'll find a lot easier to build with, with that initial assistance.
Yeah. All right, we can think about that and get back to you on that.
Okay.
What is the perspective to let non-modeling people to use this platform? Because there are some technical context to use from R. So, platform is pretty much is good to me, but meanwhile, there are some requirements of learning the commands or some other things. So what do you think about the perspective to use for non-modeling people?
So the way we envision this is that what you're using right now, what we call the model builder, is
right.
the interface for modelers to use this platform.
Right.
This interface that you're seeing right now, this is for modelers.
Yeah.
But there's another part of this application which we haven't yet developed, which I mentioned, which is sort of the model viewer, which is once you've, as a modeler, have built your model, you will be able to create a user interface for it, which is more accessible to non-modelers. Mm-hmm. And so what they will see is a set of parameters that they can control, and then they will see the results, but they won't be confronted with sort of all of the more challenging aspects of this interface. They will be given something simpler.
Oh, yeah.
But we haven't gotten to that step yet, because right now we're mainly testing, does the process of building a model do everything it needs to do, and is it user-friendly for modelers? But yes, it's very important that ultimately this platform will need to be something that's also used by non-modelers, and so that's definitely something that we're going to address.
Okay, I see.
I have a question. This is Adnan. So heRo3 is mainly now for cost-effectiveness models. Do you guys think in the future you may add the dynamic budget impacts as well in heRo3, or is it only just going to be for cost-effectiveness models?
Sorry, for adding what?
Dynamic budget impacts models?
Oh, yeah. So adding functionality for budgetary impact models, definitely something that we're interested in down the road. When that exactly happens would, of course, depend upon sort of how much demand there is for it. But I mean, that's certainly something that's a natural fit, and much of the inner workings of budgetary impact models parallel those of cost-effectiveness models. And so it's not like we would be building that functionality entirely from scratch. And so that's definitely something that's on our mind as a possibility down the road. In fact, I mean, it's not just budgetary impact models, but there's all kinds of models that could, in principle, be set up on this platform. And while we're right now focused on cost-effectiveness models, really what we're going to be interested going forward is seeing where the demand is and what kinds of models would be most useful to potential customers on this platform. Yeah, so any final questions? This is last chance before we move on and sign off. Okay, so just a final message here. If you are in need of assistance, please contact us on Slack, or you can send us an email at heRo3support@pai2.com.
So now what is Slack? Sorry.
Slack is a chat application. If you were on the initial pilot, you should have gotten an invite. If not, please send us an email and we can send you an invite.
Let's have Shana send out a blast, email blast to everybody on the user list now.
So, yeah, we will send out a new round of invites just to make sure that if you want to be on there, you can get on there. But you can either use Slack or email us and we will respond ASAP. Please feel free to contact us either if you have questions or if you need help, or if you just want to provide feedback. We value your feedback greatly, so any feedback you can provide, appreciate it. And thank you all for your continued participation in the pilot testing.